Close your eyes for a moment and picture an atom. You probably see something like a tiny solar system, a dense nucleus at the center, maybe with protons and neutrons visible as little spheres packed together. And around it, orbiting in neat, circular paths like planets around a sun, a few electrons. This picture is so familiar that it has become the universal symbol for science itself. It is on the logos of nuclear agencies and pharmaceutical companies. It decorates science classrooms around the world. It appears on warning signs and in corporate branding and in the opening credits of television programs. It is also wrong. Not slightly wrong, not a simplification that is mostly right. Fundamentally, deeply, structurally wrong, in ways that physicists understood more than 100 years ago. The electrons do not orbit the nucleus like planets around a sun. They do not have defined paths. They do not exist at specific locations at all, in the ordinary sense of the word exist. They are described by probability clouds, mathematical functions that tell you the likelihood of finding an electron in a given region, but not where it actually is. And that is just the beginning of what is wrong with the picture in your head. The atom is not a solid thing. It is almost entirely empty space. If you scaled up a hydrogen atom to the size of a cathedral, the nucleus would be the size of a grain of sand at the center, and the electron would be somewhere in the nave. But you would not be able to say exactly where, only that it was probably somewhere within a certain region. The protons and neutrons in the nucleus are themselves not fundamental. They are made of smaller things, quarks, held together by the strong force through particles called gluons. Whether quarks themselves are fundamental or whether they too are made of something smaller is a question that physics has not yet definitively answered. The atom that ancient Greek philosophers imagined, the indivisible, fundamental unit of matter, the smallest thing that could exist, is not what we found when we looked. What we found is stranger than anyone imagined. This is the story of how we found it. The word atom comes from the ancient Greek atomos, meaning indivisible, uncuttable. It was coined not as a result of experiment, but as a philosophical proposition. Around 400 BC, the Greek philosopher Democritus argued that if you kept dividing a piece of matter into smaller and smaller pieces, you would eventually reach a limit, a smallest possible piece that could not be divided further. He called this limit the atom. Matter, in this view, was made of atoms moving through a void, space that was genuinely empty. This was a remarkable intellectual achievement. Not because it was right in its details. Democritus had no experimental evidence for his atoms, and his picture of the world was wrong in many specifics. But because he had correctly identified the general shape of the question. Matter is not infinitely divisible. There is, at some level, a fundamental unit. His contemporary Aristotle disagreed. Aristotle believed matter was continuous, that you could always, in principle, divide it further, with no ultimate limit. He also believed that everything was made of 4 elements: earth, water, fire, and air, in various combinations and proportions. Aristotle was more influential. His view dominated European thought for nearly 2,000 years. The atomic theory of Democritus was preserved, discussed, but largely set aside as a minority opinion in natural philosophy. Then, in 1803, a schoolteacher from Cumberland changed the conversation. John Dalton was born in 1766 in Eaglesfield, a small village in the English Lake District. He was the son of a Quaker weaver, largely self-educated, and became a schoolteacher at the age of 12. He spent much of his life in Manchester, teaching mathematics and natural philosophy. He was not a dramatic figure. He was modest, methodical, and deeply interested in the behavior of gases and the composition of chemical compounds. He kept meticulous meteorological records for nearly 60 years. He was also, as it happens, colorblind. His study of his own colorblindness contributed to its scientific description, and for many years the condition was called Daltonism. In 1803, Dalton proposed what is now called the atomic theory of matter. His version was specific and empirically grounded in a way that Democritus's philosophical atoms had not been. Dalton's key propositions. All matter is made of atoms. Atoms of the same element are identical to each other in mass and properties. Atoms of different elements differ in mass and properties. Atoms cannot be created, destroyed, or transformed into atoms of a different element. Chemical reactions are the rearrangement of atoms. These propositions allowed Dalton to explain the laws of chemical combination that had been observed experimentally: the law of constant proportions, the law of multiple proportions, in terms of atoms combining in simple whole number ratios. His atomic theory was not immediately accepted. The idea that atoms were real physical objects rather than a useful mathematical fiction for describing chemical reactions was debated for nearly a century. Many of the most distinguished chemists of the 19th century preferred to treat atoms as calculation tools without committing to their physical existence. The definitive argument for the physical reality of atoms came, unexpectedly, from a patent clerk in Bern in 1905. Einstein's paper on Brownian motion, the random jiggling of small particles suspended in a liquid, showed that the motion could be explained precisely if the liquid consisted of molecules of a specific size, bumping into the particles from all sides. His calculation predicted the magnitude of the jiggling as a function of temperature and particle size, and the prediction matched the observations. Atoms were real. They had a definite size, and they could be counted, indirectly, through the statistics of Brownian motion. But no one yet knew what they looked like inside. By the end of the 19th century, it was known that atoms were not truly indivisible. J.J. Thomson had discovered the electron in 1897, a particle carrying negative electrical charge that could be extracted from atoms by heating or by electrical discharge. Atoms contained electrons. Electrons were much lighter than atoms. Therefore, atoms were not the smallest things. If atoms contained electrons, tiny negative particles, they must also contain something positive to balance the charge and keep the atom electrically neutral overall. But no one knew how the positive and negative components were arranged. Thomson proposed a model in 1904 that became known, somewhat uncharitably, as the plum pudding model. In this picture, the atom was a diffuse sphere of positive charge, the pudding, with electrons embedded in it at various points, the plums. The positive charge was spread throughout the atom's volume, not concentrated anywhere.
It was a reasonable guess.
It was consistent with what was known at the time. There was no evidence against it, but there was also no direct evidence for it. The way to test a model of the atom was to probe the atom, to fire something at it and see what happened. And in Manchester, starting in 1909, Ernest Rutherford and his colleagues did exactly that. Ernest Rutherford was born in 1871 in Nelson, New Zealand, the fourth of 12 children of a farmer and wheelwright. He won a scholarship to study in Cambridge, worked under J.J. Thomson, and became one of the most experimentally gifted physicists of his era. By 1909, Rutherford was at the University of Manchester, where he had established what was arguably the most productive nuclear physics laboratory in the world. He had already done important work on radioactivity, He had identified alpha and beta radiation, worked out that radioactive decay transformed one element into another, and won the Nobel Prize in Chemistry in 1908. In 1909, Rutherford suggested to his graduate students, Hans Geiger and Ernest Marsden, an experiment that seemed, at the time, almost too straightforward to be worth doing. They would take a radioactive source that emitted alpha particles, positively charged particles that Rutherford knew were equivalent to helium nuclei, with a mass about 4 times that of a hydrogen atom. They would aim a beam of these particles at a very thin sheet of gold foil, and they would detect where the particles went after hitting the foil. The expected result, based on Thomson's plum pudding model, was straightforward. Alpha particles were relatively heavy and moving fast. The positive charge in a plum pudding atom was diffuse, spread throughout its volume, and would not be strong enough to deflect a fast-moving alpha particle by more than a small angle. Most of the particles should go straight through, with perhaps a slight scattering. Geiger and Marsden set up their detectors and began firing alpha particles at the gold foil. Most particles, as expected, went straight through or were deflected by small angles. But some were deflected by large angles, and a few, a tiny fraction, about 1 in 8,000, bounced almost straight back. Rutherford later described his reaction. He said it was as if you fired artillery shells at tissue paper and they bounced back and hit you. The result was incomprehensible if the positive charge in the atom was diffuse and spread out. A diffuse positive charge could not deflect an alpha particle by a large angle. To deflect a fast-moving, relatively heavy particle like an alpha back the way it came required an enormous repulsive force. And an enormous repulsive force required an enormous concentration of positive charge in a very small region. Rutherford did the calculation. To produce the observed scattering pattern, almost all of the atom's positive charge had to be concentrated in a volume roughly 10,000 times smaller than the atom itself. The atom was not a uniform sphere. It was mostly empty space, with almost all of its mass and positive charge concentrated in a tiny, dense nucleus at the center. In 1911, Rutherford published his nuclear model of the atom. The plum pudding was wrong. The atom had a nucleus. Rutherford's nuclear model immediately created a problem. In classical physics, an electron orbiting a nucleus would be continuously accelerating, curving inward, always changing direction. Accelerating charges radiate energy. An orbiting electron should continuously radiate electromagnetic energy, losing energy as it does so, spiraling inward, and crashing into the nucleus within a fraction of a second. All atoms should be instantly unstable. Matter should not exist. Obviously, matter exists. Atoms are stable. Electrons do not spiral into nuclei. Something was wrong with classical physics, not with atoms. The solution came from a young Danish physicist named Niels Bohr, who visited Rutherford's Manchester laboratory in 1912 and spent 4 years working out a model that could explain atomic stability. Bohr's key insight, borrowed from the emerging quantum theory of Max Planck and Albert Einstein, was that the rules governing the atom were not the rules of classical physics. Electrons could only occupy certain specific orbits, corresponding to specific energy levels. They could not orbit at arbitrary distances from the nucleus. And while in these allowed orbits, they did not radiate energy. They could jump from one orbit to another, emitting or absorbing a photon of specific energy equal to the difference between the energy levels. But they could not transition continuously. They jumped discretely from one level to another. no in between. The Bohr model was a partial success. It correctly predicted the wavelengths of light emitted by hydrogen atoms, a precise confirmation that had eluded previous theories. It explained why atoms were stable. Electrons in their lowest orbit had nowhere to fall to, no lower energy state available. But it was also clearly incomplete. It worked well for hydrogen with its single electron, and poorly for more complex atoms. And it gave no explanation for why electrons were confined to specific orbits. It stated the rule, but did not explain the rule. The explanation required a more radical departure from classical thinking. In 1924, a French physics student named Louis de Broglie proposed something that seemed, to many of his contemporaries, like science fiction. If light, which was known to behave like a wave, could also behave like a particle, as Einstein had shown with the photoelectric effect in 1905, then perhaps particles, electrons, protons, atoms, could also behave like waves. De Broglie's proposal was not simply an analogy. He gave a precise mathematical relationship. Every particle has an associated wavelength, given by Planck's constant divided by the particle's momentum. The smaller the mass and the lower the speed, the longer the wavelength. This was a testable prediction. If electrons had wave properties, they should produce interference patterns, the characteristic light and dark bands that appear when waves pass through narrow slits. In 1927, Clinton Davison and Lester Germer at Bell Laboratories in New York demonstrated exactly this. Electrons passing through a crystal produced interference patterns. Electrons were waves. They were also particles. They were both, depending on how you looked at them. The mathematical framework that incorporated de Broglie's wave-particle duality and resolved the problems of the Bohr model was developed in 1925 and 1926, primarily by Werner Heisenberg and Erwin Schrödinger, working independently and from different mathematical starting points. Their two formulations, matrix mechanics and wave mechanics, were later shown to be mathematically equivalent. Together, they constituted quantum mechanics. In quantum mechanics, the state of an electron is described not by a position and a velocity, but by a wave function, a mathematical object that encodes the probabilities of finding the electron in different states when measured. The wave function evolves according to Schrödinger's equation. When a measurement is made, the wave function collapses to a specific outcome. And here, in the interpretation of the wave function, physics encountered a problem. It has not fully resolved in 100 years. What does the wave function mean? Is it a description of the electron's actual state, what is really out there before measurement? Or is it merely a tool for calculating probabilities, a recipe for predicting outcomes, with no claim to describe reality as it is? The Copenhagen interpretation, associated primarily with Niels Bohr, held that quantum mechanics was a complete theory, that the wave function gave the most complete possible description of reality, and that questions about what the electron was doing before measurement were not physically meaningful. Einstein disagreed. He spent years arguing that quantum mechanics was incomplete, that it must be missing something, some hidden variable that would restore determinism and realism to physics. The debate between Bohr and Einstein, carried on over decades in print and in person, never fully resolved in Einstein's lifetime, is one of the greatest intellectual disputes in the history of science. Einstein's most famous dismissal, "God does not play dice." Bohr's reported response, "Stop telling God what to do." In 1964, John Bell derived a mathematical theorem that allowed the dispute to be settled experimentally. If hidden variables of the type Einstein imagined existed, Measurements on entangled particles would satisfy certain inequalities. If quantum mechanics was complete, as Bohr claimed, the inequalities would be violated. Experiments conducted beginning in the 1970s and with increasing precision through subsequent decades consistently violated Bell's inequalities. The most recent definitive experiments were conducted in 2015 and 2022, closing the remaining experimental loopholes.
Einstein was wrong.
Bohr was right. Quantum mechanics is not incomplete in the way Einstein imagined. God, or at least the universe, does play dice. The nucleus of an atom consists of protons and neutrons. Rutherford discovered the proton in 1917, demonstrated that it was a constituent of atomic nuclei. James Chadwick discovered the neutron in 1932. These seemed for a time to be fundamental particles, the ultimate constituents of matter, with no internal structure. They are not. In the 1950s and 1960s, as particle accelerators became more powerful, physicists began colliding protons and electrons with enough energy to probe their internal structure. The results were surprising. Deep, inelastic scattering experiments, electrons fired at protons at very high energy, showed that the proton was not a uniform object. The electrons sometimes bounced off hard, point-like constituents inside the proton, in a manner that recalled Rutherford's gold foil experiment half a century earlier. Something hard and small was inside the proton. These constituents were called quarks, in a name proposed by the physicist Murray Gell-Mann, borrowed from a line in James Joyce's Finnegan's Wake. 3 quarks for muster mark.
Quarks are peculiar.
They carry fractional electric charge, 1/3 or 2/3 of the charge of an electron. They come in 6 types, called flavors: up, down, strange, charm, bottom, and top. A proton consists of 2 up quarks and 1 down quark. A neutron consists of 1 up quark and 2 down quarks. Quarks are never found in isolation. The force that holds them together, the strong nuclear force, mediated by particles called gluons, becomes stronger as quarks are pulled apart. You cannot pull a quark out of a proton. The energy you put in to try to separate them creates new quark-antiquark pairs before the quarks can be separated. Quarks are permanently confined. Whether quarks themselves have internal structure, whether there is something inside the quark, is not currently known. The experimental evidence is that they are point-like. No internal structure has been detected down to scales 1,000 times smaller than the proton itself. But absence of evidence is not evidence of absence. Let me try to make the scale of all this concrete. A hydrogen atom consists of 1 proton and 1 electron. The diameter of a hydrogen atom, the region in which the electron is likely to be found, is roughly 100 picometers, or 1/10,000,000th of a meter.
The diameter of the proton,
the nucleus of a hydrogen atom, is roughly 1 femtometer, or 1/quadrillionth of a meter. 100,000 times smaller than the atom. If you expanded the atom to the size of a cathedral, say 100 meters across, the proton would be 1 millimeter in size, a grain of sand at the center. The electron would be somewhere in the nave, but you could not say exactly where. You could say that there was a 90% chance it was within a certain volume. You could say that it was more likely to be found near the center than near the walls. But you could not say it was at a specific location because, in the quantum mechanical description, it does not have a specific location until it is measured.
the rest of the cathedral is empty.
Not filled with something very thin, not filled with fields or forces in any material sense. Empty. The space between the nucleus and the electron is genuine void. This is what matter is. the desk you may be sitting at, the hand you could hold in front of your face, the air you are breathing. All of it is atoms. All of those atoms are almost entirely empty space, with tiny nuclei at their centers and electrons somewhere in the vast, empty regions around them. The reason matter feels solid, the reason your hand cannot pass through the desk, is not because the atoms are packed together. It is because of electromagnetic repulsion between the electron clouds of adjacent atoms, and because of the Pauli exclusion principle, which prevents electrons from occupying the same quantum state. The solidity of matter is an emergent property of electromagnetic and quantum effects, not of atoms being physically touching or packed together.
You are not solid in the way you think you are.
Nothing is. The most complete description of matter and its fundamental constituents that physics currently possesses is called the Standard Model of Particle Physics. The Standard Model describes 12 fundamental particles of matter, 6 quarks and 6 leptons, which include the electron and its heavier cousins, plus 3 types of neutrino. It also describes the force-carrying particles, photons for electromagnetism, W and Z bosons for the weak nuclear force, gluons for the strong nuclear force. And it includes the Higgs boson, discovered in 2012 at the Large Hadron Collider, which gives mass to fundamental particles through the Higgs field that permeates all of space. The Standard Model is extraordinarily successful. It has made predictions that have been confirmed to extraordinary precision. The magnetic moment of the electron, for instance, matches the theoretical prediction to more than 10 decimal places, making it one of the most precisely confirmed predictions in the history of science. It is also certainly incomplete. It does not include gravity. There is no quantum theory of gravity, as discussed in the episode on gravity. It does not explain dark matter, the mysterious substance that makes up roughly 27% of the universe's energy mass content, whose gravitational effects are clear, but whose nature remains unknown. It does not explain why there is more matter than antimatter in the universe. It does not explain the observed masses of the neutrinos. The Standard Model is the best description of the atom, and of everything below the atom that currently exists. It is not the final description. Physics knows this. The search for what lies beyond it, the deeper theory of which the Standard Model is presumably a limiting case, is ongoing. The atom that Democritus imagined was indivisible. The atom that Dalton described was a fundamental building block. The atom that Rutherford probed was mostly empty space with a nuclear heart. The atom that quantum mechanics described was a probability cloud, not a solar system.
And below the atom,
Quarks and gluons and the Higgs field and the Standard Model and questions that do not yet have answers. The deeper you look, the stranger it gets. Close your eyes again. Try to picture an atom. Not the solar system, the real thing. At the center, a nucleus. A tiny, dense region containing almost all the mass, held together by the strong nuclear force against the electromagnetic repulsion of its positively charged protons. The nucleus is 1/100th of a 1,000th of the width of the atom. Around it, vast, empty space. Not truly empty, permeated by electromagnetic fields, by the Higgs field, by the quantum vacuum with its fleeting virtual particles. But empty of matter, empty of anything you would call substance. And somewhere in that space, not orbiting, not moving on a defined path, not even having a defined location, the electron, described by a wave function, a probability amplitude spread through space. When you measure it, you find it somewhere specific. Between measurements, it is in a superposition, existing in a precise mathematical sense in multiple places simultaneously with different probabilities. The nucleus itself is made of protons and neutrons. Each proton and neutron is made of quarks, 3 of them, bound together by gluons, confined so completely that they cannot be extracted. The quarks may or may not have internal structure. This is matter. This is the thing you are made of. Every cell in your body, every protein, every molecule, every bond, all of it is atoms, and all of those atoms are this: mostly empty space, a vanishingly small nucleus, and electrons described by probability clouds. The solidity of the world, the reassuring fact of the desk under your hand, the floor under your feet, is an emergent property. It arises from quantum mechanics and electromagnetism. It is real, but it is not what it appears to be. Democritus was right that there is a fundamental level. He was wrong about almost everything else. Dalton was right that atoms are real and that chemistry is their rearrangement. He had no idea what they looked like inside. Rutherford was right that there is a nucleus. He had no idea what was in it. Bohr was right that quantum rules govern the atom. He could not fully explain why. Each one stood at the edge of knowledge and looked further than anyone before them. Each one was standing on the shoulders of everyone who came before. And each one, when the next generation looked, turned out to have been standing somewhere that was not yet the bottom. We do not yet know if we have found the bottom. We do not yet know if there is a bottom. But every time we have looked more carefully, from Democritus to Dalton, from Dalton to Thomson, from Thomson to Rutherford, from Rutherford to quarks and the Standard Model, the world has been stranger, smaller, emptier, and more mathematically beautiful than we expected. The picture in your head was wrong. The real one is better.